All right, let's do part 5, which entail us taking a piece of information, drawing a sketch, and then writing the limit expression of the Riemann sum and the definite integral form. And I'll have you find the net signed area using the calculator. So let's start with the first one, which is just a constant function. So my sketch is just going to be the line y equals 4 right here. And I put it on the interval from 0 to 2, so it is this section right here. So the limit expression of the Riemann sum will be the limit as n goes to infinity, the summation from I equals 1 to n, I equals 1 to n, and that part that I just wrote in red will actually hold for every single problem. Limit as n goes to infinity, summation from I equals 1 to n. So what's different for each problem is the actual function, the width of the interval, the starting point. So the width of this interval is 2, which means that each delta x is going to be 2 over n. So I multiply my function by 2 over n. And my function here is just 4, so I have 4 times 2 over n. There's no x value in my function, so I can't input my x value that's the right-hand endpoint of my ith subinterval as taught in the lesson. So we'll get to that on the next section, on the next problem. The definite integral form, I just need to integrate the function 4 from 0 to 2. And you could do this on your calculator, but this is a pretty easy one to do by hand. So I will apply the fundamental theorem of calculus to integrate 4 to 4x, going from 0 to 2, evaluated at 2, subtract out evaluating at 0, and my final answer is 8. Next problem, I will start with the graph. I have y equals 2x, which is this function right here. My interval is 1 to 3, so I shade in that region. Then I need to complete my sigma notation, my limit, my infinite limit of the Riemann sum. So I have an interval of 2. 3 minus 1 is 2. So I have delta x of 2 over n. I have the width of 2 dividing into n rectangles. And then my function is 2x. So I'm going to have 2 times x, and my x value is going to be my left-hand point, 1, and add to that my delta x times I. So it'll be 1 plus 2i over n. And just since you can't read that, that says 1 plus 2i over n. And then I multiplied that by 2 because this is twice x. So the integral is going to be the integral from 1 to 3 of the function 2x dx. And I'll go ahead and do this one using the fundamental theorem of calculus as well. 2x integrates to x squared, evaluated from 1 to 3, gets me 9 minus 1, which is 8. So there are 2 more problems here. First one is f of x equals 2x squared minus 1. So I have a quadratic that is shifted down by 1 and made narrower from my original quadratic. And I'm integrating this on the limits of 2 to 4, which will be, say, here to here. So this section that I'm integrating is sort of over here. Okay? It's all entirely above the x-axis. So the limit expression of the Riemann sum, we start again with the limit as n goes to infinity, summation from I equals 1 to n. The width of my interval is once again 2 because 4 minus 2 is 2. So my delta x is 2 over n. My function is 2x squared minus 1. So I'm going to have 2, my x value squared minus 1, like that. That's a squared up there. The x value always starts at the left-hand side of my interval, which is 2, and then I add my delta x, 2 over n times I, so I get 2i over n. Then, when I write it in integral form, I'm integrating from 2 to 4, 2x squared minus 1 dx, and I'll go ahead and do this one by hand again. I guess none of these are super difficult to do by hand, so I think it's better to teach you to do it by hand using the fundamental theorem of calculus. So integrating 2x squared, I get to 2/3 x cubed minus x, and evaluate that from 2 to 4 gives me, let's see, 4 cubed is 64 times 2 is 128, so I have 128 over 3 minus 4, That whole expression is then subtracting out big F of 2, so 2 cubed is 8. 2 times 8 is 16. I have 16 thirds minus 2. I know that's falling off the screen there, but let's see if I can fix this up. So 128 over 3 minus 16 over 3 is 112 over 3. And then I have negative 4 minus a negative 2. So negative 4 plus 2 is negative 2. And that gives me 112 over 3 minus 6 over 3 is 106 over 3. And that is your final answer. Last problem here, 2x minus x cubed. If I factor that, I get x times 2 minus x squared. So I have zeros of this function at 0, and then at, that's 2 minus x squared, so 2 will be equal to x squared at plus or minus rad 2. So I have 3 zeros here. I have a negative leading coefficient, so my graph looks like that. And then I'm integrating from 1 to 3. And when I integrate from 1 to 3, what I get is an interval that looks from like here to here. So I have sort of one section above the x-axis and one section below the x-axis, but that shouldn't make any difference. I'm then taking the limit as n goes to infinity of the summation of I equals 1 to n. And my function is 2 times x, so I'll start here with 2. My x value is the left-hand side of the interval, 1, plus the width of the interval, which is 2, I over n, and I'm not squaring that or anything. I have 2 times this x minus x cubed, and x, once again, is 1 plus 2i over n, and that is cubed. And then I multiply this by delta x, which is the width of 2 divided by n. So I then need to write my integral, which is going to be the integral from 1 to 3 of 2x minus x cubed dx. And then I'll go ahead and evaluate that using the fundamental theorem of calculus. When I integrate, I get x squared minus x to the 4th over 4. Evaluating from 1 to 3 gives me 9 minus 81 fourths, and then subtract out 1 minus 1 fourth. So when I simplify all that, I'm going to get 9 minus 1 is 8, and then negative 81 fourths minus a negative 1 fourth is going to be minus 80 fourths, which is 20. So 8 minus 20 is negative 12.